Hi everyone. In this module, we have to learn the spectroscopy applications in inorganic chemistry. Here, spectroscopy is the study of interactions between the matter and electromagnetic radiation. Consider examples of this spectroscopy. The IR spectroscopy is concerned with study of absorptions of infrared radiation which causes vibrational transition of bands in molecule. So it is called the vibrational spectroscopy. This spectroscopy mainly used to identify the functional group. It also gives informations like number of bond, stereos, isomer, the atomic arrangement in the molecule. In that, infrared radiations of the region is this electromagnetic radiation, the arrangement of all the different types of electromagnetic radiation in the increasing order of their wavelength or decreasing order of their frequency. Generally, the infrared region starts from here 0.75 micrometer to 1000 micrometer. These infrared regions are broadly classified into near IR region, mid IR region, and far IR region. In that near IR region, wavelength starts from 0.8 to 2.5 micrometer. The wave number is 12,500 to 4,000 per centimeter. In this near IR region, infrared with UV radiation and gives extra intervalence charge transfer band on higher spectra due to delocalization of this electron. In mid IR region, the wavelength starts from 2.5 to 5 micrometer. The wave number is 4000 to 200 per centimeter. In mid IR region is appropriate for the IR spectroscopy because it gives fully IR peak on IR spectrum. It is used to 2.5 to 5 micrometer wavelength in IR spectroscopy. Next we consider the far IR region. The wavelength starts from 50 to 1000 micrometer. The wave number is 200 to 10 per centimeter. In that far IR region is also closer to the radio wave region and sometimes bandly interact and form extra unwanted band spectra on the IR spectrum. What is the basic principle of this IR spectroscopy? When that IR radiation is interact with the sample molecule which absorb the and applied quantized IR light which is matched with the internal vibrational frequency of the molecule and other residual frequencies are transmitted via the sample. Due to the absorptions of IR radiation, the net change of dipole moment in a molecule is occurred and causes vibrational of bands in the molecules like stretching and bending vibration. The transmitted light is detected by the detector and IR spectrum interrupted on the computer screen by analysis of the transmitted light. Just to see that here IR radiation, this samples, this absorbs specific frequency, what we are getting here transmitted light. In the graph plotted wave number versus percent of transmission. The position of the atoms in a molecule due to net change of dipole moment, change in amplitude of the molecular vibration, what we are getting here, stretching and bending vibrations. This is the FTIR, means Fourier transform spectrophotometer. This is what the source, IR sources. This is the moving mirrors are there. One is stationary mirror and another one is moving mirror. When this beam of light, it undergoes splitting. This is the sample. Once it passes this IR radiation, it passes through these samples. That detector, it catches that frequencies in that computer on that screen. What we are getting here, graph or peaks. How it is works this FTIR spectrophotometer. The source energy strikes the beam splitter and produces two beams of roughly the same intensity. One beam strikes the fixed mirror and return to the beam splitter. The other beam goes to the moving mirror. When these two beams meet again at the beam splitter, they recombine. The recombined beam passes through the sample. The radiation source. Here, NE or HT glower or global source which produce the mid-IR region. These molecular vibrations, that molecular vibrations, two types of molecular vibrations, the stretching vibrations, that higher frequency, and another one bending vibration, that lower frequency. That stretching vibrations, two types of stretching here, symmetric stretching and asymmetric stretching. In that symmetric stretching, both the direction is in that same direction. Both the stretching in that same direction. Just you see that arrow mark here, both the stretching in same direction. But here, stretch is in that opposite direction. Stretch in that opposite direction. Next, consider these bending vibrations in that lower frequency, in plane bending and out of plane bending. In plane bending, scissoring bending and rocking bending. In out of plane bending, the twisting bending and wagging bending. Here, number of vibration is usually more than the number of stretching vibrations in IR spectrum. In that, stretching vibrations involves continuous changing. Here one is the symmetric stretching. Already we see that symmetric stretching, and another one is asymmetric stretching. In symmetric stretching, the bond length increase symmetrically. The bond length increase symmetrically. In asymmetric stretching, here the bond increase and the other one is decreased. One bond of the atom is increased and another one is decreased at the same time without changing the bond angle. That bending vibration, that scissoring, is the movement of two atoms toward and away from each other. So, bond angle decreased and increased with time. Next we consider in that rocking in which good bond angle is maintained but bond moves within the same plane. We are changing angle between the group of atoms. In that wagging, in which both atoms move one side of the plane, changing angle between the plane, a group of atoms. Twisting, in one atom is above the plane and other is below the plane, changing angle between the plane, two groups of atoms. Here, what are the conditions or criteria to absorb IR radiation? When applied infrared frequency in equal to natural frequency of vibrations, then the absorption takes place and a peak is absorbed. Only molecule gives IR absorption. Molecule must have a dipole moment. The mode of vibrations of the molecule should not be center of symmetry. The molecule should be polar. Generally, these conditions it obeys that IR radiation. One important here, it is not necessary for a compound to have a permanent dipole moment to be IR active. The modes of molecules with respect to electromagnetic radiation. Here, what are the modes are there? Here, translational modes, rotational modes, and vibrational modes. Here, in that the total number of degrees of freedom. Here, the translational, rotational, and vibrational. The sum of translational, rotational, vibrational degrees of freedom. That is what? Total number of degrees of freedom. The vibrational degrees of freedom is equal to 3n minus translational plus rotational degrees of freedom. Vibrational degrees of freedom is equal to 3n minus 3 plus rotational degrees of freedom. For a linear molecule, the vibrational degrees of freedom is equal to 3n minus 3 plus 2. What we are getting? 3n minus 5. That is number of atoms in the molecule. It is what? Non-linear molecule. In vibrational degrees of freedom, what we are getting here? 3n minus 6. That is for that non-linear molecule. 3n minus 5. That is for that linear molecule. Just we consider examples of this here. CO. CO means that is carbon monoxide. Here C 3 into 3, what we are getting here? 4. Here 4 means what? That is non-linear molecules. But we consider this here vibrational degrees of freedom of this water molecule is here 3 into 3 minus 6 is equal to 3. That is what? This is the way to find out that here linear molecules or non-linear molecule based on that vibrational degrees of freedom. Here, how to calculate the vibrational frequency? Vibrational frequency is calculated. Mu bar is equal to 1 by 2 pi c root of k by mu. Here mu means here m1, m2 by m1 plus m2. Here mu means that is frequency in per centimeter. C means velocity of light. K is rate constant. Here m is atomic masses. Mu means that is reduced mass. Here for single bond, that K value or force constant is 5 into 10 to the power of 5. For double bond, 10 into 10 to the power of 5. For triple bond, 15 into 10 to the power of 5 time per centimeter. Just to see here, carbon-carbon single bond, double bond and triple bond, the increase in the K value. For this single bond or sigma bond, what we are getting here? 1200. For this double bond, 1650. For this triple bond, 2150. Is increasing mu value. Here, for CH, 3000. Carbon-carbon single bond, 1200. Containing oxygen with carbon 1100, carbon chloride 750, carbon bromide 650. What is IR spectrum? The IR spectrum is the graphical plot of transmittance versus vibrational frequency of wave number. These are representations of this IR spectrum. Here, transmittance is equal to here intensity of transmitted light by intensity of that incident light. I by I naught. Here mu bar is equal to 1 by wavelength. This IR spectrum, the functional group region and fingerprint regions is the very important. In that the functional group region appeared 4000 to 1500 per centimeter identifies the functional groups. Like different functional groups are there: aldehydes, ketone, carboxylic acid, alcohols, phenols, ethers, amines, and some others, esters. These are all what? Functional group. Identify the functional groups with the consequence of changing stretching vibration. Only stretching mode of vibration, so that region contains few peaks. So the pattern of peak is easy to analyze because stretching vary within a narrow range. What we are getting: sharp, broad, strong, medium peaks are obtained. In that, fingerprint region starts from 1500 to 5500 per centimeter. It identifies the extra molecules within the consequence of changing bending vibration. Stretching and bending both are occurred, but bending is more than stretching. The pattern of peak is more complicated due to complex vibration, which creates unique IR band to distinguished compound. What we are getting: sharp and weak peaks are obtained. Is the peak of functional group, is the shape, width of peak, that is intensity, that is height of peak. Here in that shape, broad and sharp peak are coming here due to hydrogen bonding or due to the presence of these water molecules. What we are getting: broad peaks are up here. That intensity, it explains the height of the peak. It is strong, medium and weak. That strong means strong bond covers most of the y-axis. The medium band falls to about the half of the y-axis. A weak band falls about to 1/3 or less of the y-axis. What are the factors affecting the peak intensity? Here, that peak intensity depends on this what? Electronegativity difference and polarity and dipole moment is directly proportional to that more intense peak. If electronegativity difference increase, the intensity of peak is also increases. Polarity of this molecule increase, it gives more intense peak. Dipole moment is also directly proportional to that more intense peak. Is the some samples generally we are giving to that how this IR spectrum it appears like that. What are the factors affecting the vibrational frequencies of the functional group? Here, effect of different mode of vibrations. Here, the frequency of stretching is higher in bending. Reduced mass of atom is inversely proportional to vibrational frequency. More vibrational frequency is equal to force minus constant. In that electronic effect, the conjugation resonance is directly proportional to the vibrational frequency. Hydrogen bonding effect is inversely proportional to the vibrational frequency. Multiplicity of bond means number of bond is directly proportional to the vibrational frequency. Nature of hybridization, the percentage of S character is directly proportional to the bond strength, directly proportional to or inversely proportional to the bond length, and directly proportional to that stretching frequency. This is what we are increasing the bond strength. Here carbon-carbon bond dissociation energy is less because it is having only sigma bond. But in case of carbon-carbon double bond dissociation enthalpy is increases. It is higher in that carbon-carbon triple bond. Here decreasing frequency are mentioned here. How to interpret or analyze IR spectra? Here, IR spectra is not generally used to determine the whole structures of unknown molecule. IR spectra is great for identifying certain specific group. Here, an overview of the IR window from 4000 to 500 per centimeter with various regions of interest highlighted. Just you consider here, this is the graph of this wave number versus percent of transmittance. In that regions, is in between that 3500 to 3000 regions. What we are getting here, OH stretching and all kinds CH stretching. and 3300 to 3500 that NH stretching. In 2250 to 3100 that is what CH stretching. In 3000 region that is alkynyl CH stretching. Less than 3000 that is alkyl CH stretching. In these regions like 2100 to 2000 to 60 per centimeter that is carbon nitrogen and carbon carbon triple bond. In this region 1650 to 1800 per centimeter it is CO stitching, and this 500 to 1000 per centimeter it is a fingerprint regions. In that fingerprint regions it is having a different molecules we are going to predict it based on that what of fingerprint regions. Basically 80% of the most useful information for our purpose can be obtained by looking at 3600 to 1600 per centimeter specific area of spectrum. The peak from 500 to 1400 that is fingerprint region comparatively less useful. And more compressed overview look like this. Here zone 1. This IR peak generally we are going to classify into zone 1, zone 2, zone 3 and zone 4. Here in that zone 1 region starts from 3600 to 2700. Here common symbols of bond here X, H. Examples of this bond functional group here OH bond, CH bond and NH bond. Here zone 2 2700 to 1900. Here carbon X triple bond X. Here carbon triple bond nitrogen, carbon triple bond, carbon bond. In zone 3 1900 to 1500. Here X double bond O, X double bond X. Here CO bond or CC bond generally predicted. In 1500 to 1000 what we are getting here CO bond and CC bond. Here in this example we are giving here X means what, that is oxygen or carbon or nitrogen. In that zone 1 OH stretching at 3650 to 3200 per centimeter with strong intensity and a broad U elongated shape. The terminal alkynes, the CH bond stretching 340 to 3250 per centimeter with a stronger, sharper peak. That NH stretching mainly occurred in the primary and secondary amines. The primary amines stretching 3500 to 3200 with the two signals, and that secondary amines the stretching at 3500 to 3200 with one signal. This weak intensity sharp line. This is what the medium intensity and broad shape. The CH stretching at 3100 per centimeter with weak intense and sharp peak. The CH stretching at 2900 to 2800 per centimeter with medium intense or sharp peak. This zone 2, in zone 2 here carbon triple bond stretching at 2200 to 2000 per centimeter with variable intense and sharp peak. The C triple bond N bond stretching at 2260 to 2000 to 20 per centimeter with variable intense and sharp peak. In zone 3, the carbon oxygen bond strength stretching peak for aldehyde at 2200 to 2000 per centimeter, ketone at 1700 to 1725 per centimeter, carboxylic acid at 1715, for esters is 1750 to 1735. These are all what different functional group, it appears different IR peak. Okay, these are all just you see that aldehydes here, this peak appeared, that propanol, this ketones, esters, carboxylic acid, In that ketones here to propanone and acetophenone in ester, ethyl acetate and methyl benzoate, carboxylic acid, butanoic acid or benzoic acid. These are all the carboxylic acids. These are all the esters, ketones, aldehydes. Okay. These what almost always the strongest peak on the spectrum. The C double bond C bond stretching peak at 1062 to 1600. The carbon-carbon bond stretching for aromatic compound is 101510 to 101450 per centimeter. In that zone 4 carbon-carbon stretching and carbon-oxygen bond stretching peak appears. These are all different IR peaks from this different functional group. Here just we consider these the representations of this peak. Just we are going to find what is the peak of this and what is the peak of this, and this is the function group. What is the peak of these molecules? Okay, these are all find out here. What are the applications of this IR spectroscopy? This IR spectroscopy generally to find identifications of this organic compound. It is useful to study structural determinations. It is useful to identifications of functional group. It is very useful to studying the progress of reaction. By using IR spectroscopy to distinguish between two types of hydrogen bonding, study of keto-enol tautomerism, study of cis-trans isomerism, study of air conformations analysis, determinations of impurities in the compound, and presence of water molecules present in the samples. These are all what? Applications, major applications of this IR spectroscopy. What are the limitations of this IR spectroscopy? That IR spectroscopy cannot determine the molecular weight of the compound, does not give information about the relative position of different functional groups in a molecule. From the single IR spectra of an unknown substance, it is not possible to know whether it is pure or a mixture of compound. The sample cells are made of halogen salts which are susceptible to moisture. Gas samples cannot be analyzed as the lack of sensitivity. Thank you.